Welcome to today's Explainer, students. Today we are looking at digital logic design, specifically focusing on the internal architecture of DRAM. Have you ever wondered what's truly going on under the hood of your computer when a program loads? In simple words, your computer is performing millions of logic operations to move data from long-term storage into the incredibly fast-working memory known as dynamic random access memory. Let's demystify exactly how this works. Here is the agenda for our explainer today. We'll start with why we need DRAM, take a look inside the physical memory stick, examine the microscopic 1T1C cell, cover the reading, writing, and refreshing logic, and finally, look at architectural speed optimizations. This follows a very standard syllabus sequence, so pay close attention. All right, Section 1, why we need DRAM and the speed bottleneck. Students, remember this point. Solid-state drives are fantastic for permanent storage, but when the CPU actually needs to execute a program, the SSD is simply way too slow. It creates a massive bottleneck. Look at this comparison here. This is a very commonly asked question in Vivas. Accessing a section of an SSD takes about 50 microseconds, but reading from a DRAM cell, just 17 nanoseconds. That is 3,000 times faster. To visualize this, it's literally like comparing a slow tortoise to a Mach 3 supersonic jet. If the CPU had to wait for the SSD tortoise, your entire system would hang. To put that into perspective, consider a heavy video game seamlessly moving 3D models into DRAM during a loading screen. Just imagine without DRAM, playing a game would be 3,000 times slower. Every single frame relies on this high-speed data shuttle. Moving to Section 2. Inside the memory stick. We are going to transition from macro to micro here, zooming in from the DIMM module on your motherboard right down to the silicon. Now, this physical hierarchy is extremely important for your semester exams, so please note this down. A DIMM stick holds 8 microchips. One chip contains a 2 GB die. That die is split into 8 bank groups, and each group has 4 banks. That gives us 32 independently operating banks, and inside each bank, it's a massive 2D logic array of rows and columns. Make sure you draw this exact hierarchy in your exam. Inside just a single 2 GB die, we find a staggering 17 billion individual memory cells. Yes, 17 billion. Just imagine the sheer density of digital logic packed into that tiny chip, and your computer relies on every single one of them working perfectly. Section 3, the microscopic memory cell. Let's zoom in to the absolute smallest unit of this array, the 1T1C architecture. This is a foundational concept. What is 1T1C? Mark this as a short note question. It stands for one transistor, one capacitor. The transistor is basically a logic gate to access data, and the deep trench capacitor is a microscopic bucket that stores one bit of data as an electrical charge. The insulator trapping those electrons is literally just a few atoms thick. Let's look at the working principle. In simple words, a charged capacitor at 1 volt gives us a binary 1. An empty capacitor at 0 volts gives a binary 0. The word line connects to the transistor gate to turn it on, and the bit line acts as the data bus. Students usually confuse these two wires, so remember, word line is for control, bit line is the pathway for data. But think about this from a digital design perspective. With 17 billion of these tiny cells laid out in a massive grid of 65,000 rows by 8,000 columns, how does the CPU pinpoint just one specific cell? The answer is memory decoding. The CPU sends a very precise 31-bit address, exactly like a GPS coordinate. First, bits select the bank group. Then a 16-bit address goes to a row decoder to activate one row. Finally, a 10-bit address goes to a column multiplexer to select exactly 8 bits. This is a classic example of address line logic in action. Okay, Section 4, reading, writing, and refreshing. Let's examine the physical mechanics of how we manipulate voltages to actually move data. Here are the step-by-step mechanics for a read operation. Mark this as a 5-mark question. First, we precharge bit lines to exactly 0.5 volts. Second, activate the row. Third, the tiny capacitor slightly alters that 0.5 volts up or down. Fourth, the sense amplifiers detect this tiny voltage perturbation and drive it to a full 1 volt or 0 volts. Finally, the multiplexer routes the 8 bits to the CPU. This delicate process happens millions of times a second. Now, compare that to writing data. Sense amplifiers are used for reading. They detect tiny voltage changes. But for writing, we use a write driver. It uses a strong signal to forcefully override the bit line voltage, actively forcing the tiny trench capacitor to accept a new 1 volt or 0 volt charge. Reading is delicate, writing is forceful. Now, why is it called dynamic RAM? Because capacitors leak charge. To prevent data loss, the system must perform a refresh operation every 64 milliseconds. It takes about 3 milliseconds for the chip to systematically close, pre-charge, and reopen all 65,000 rows. If asked in a interview why DRAM needs refreshing and SRAM doesn't, this constant electrical leakage is the exact reason. Finally, Section 5, Achieving Incredible Speeds Through Architectural Optimizations. Let's see how engineers overcome these delays to make DRAM so incredibly fast. Engineers use a few brilliant tricks here. First, row hits. If a row is already open, the logic skips the pre-charge steps completely. This is exactly why we use 32 independent banks, so multiple rows can stay open. Also, we break massive grids down into 1024 by 1024 sub-subarrays to shorten the physical wires and reduce resistance. We even use cross-coupled inverters to actively cancel out electrical noise. Top-tier logic design right there. Furthermore, we use a burst buffer. Instead of fetching 8 bits one by one, the chip grabs a massive 128-bit chunk of sequential data all at once, caching it temporarily. This allows the memory to fire off data to the CPU in one rapid burst. In simple words, it fetches in bulk to save time. Thanks to all these architectural optimizations, these microscopic banks can handle an absolutely staggering 4,800 million read and write requests every single second. It is a true symphony of digital engineering. So, as we wrap up today's explainer, I want to leave you with a thought. We are managing 17 billion physical cells at nanosecond speeds, executing billions of operations just to move data. How much further can we push the laws of physics? What new logical architectures will you, the next generation of engineers, need to design to break these limits? It's a fascinating question. Revise your notes thoroughly, and I'll see you in the next session.